When you come to class, please know your schedule because there's going to be a phytoplankton growth experiment, and that means that you'll form groups of hopefully 4, and somebody needs to come every day so that we get a time course with this experiment. So just bring your calendars. Next week's lab should be pretty relatively short to compensate that the fact that we're going to expect you to come for about 20 minutes. When you do come, if you come on time, you'll get out on time.
Is that going to screw up with the Tuesday lab group?
No, they're going to start on Tuesday, so they'll be more restricted for their Monday sampling, just so that we don't have a backup in terms of instrumentation and equipment. So I sent Max a draft schedule, but I don't know if your email is working yet. Okay, so we'll figure that out next week, but just come with your schedule so you know what you're doing. What you're going to do in the lab today is what you're going to do for the practicum. So make sure you understand what you're doing in the lab today. And if you go to the website, there's a file that has all of this so that you know exactly what the breakdown is for the practicum. And that's the 25th and the 26th of April during your regular lab period. So today is going to be very much like the practicum. What I'd like to do is just briefly review Beer's Law and show you a group in section 2 did a kind of a neat experiment, and I'd like to show you the results of that. And then I want to talk about nutrients and how we're going to measure phosphate today. And also serial dilutions, which again are another workhorse of chemists. And you'll be doing serial dilutions today. So here's the percent transmission versus the dye. And one of the things that gets people very confused is that when we talk about blanks, there is an instrument blank, which you do with millicu water. And what you're doing, and so in simple reads, you push that 0. What you're doing is you're telling the spectrophotometer that when there's pure water there, 100% of the light is being transmitted. So you're setting the scale. So that's one type of, I call it the instrument blank. And so you're forcing the instrument to say, with water, or it could be acetone or whatever, you're saying when you get this reading, that means 100% of the light is getting through for this situation. Here's a practical question. If this is a 1 centimeter cell, here's a nice linear absorbance versus dye. If you have a reading out here that measures 0.7 in a 1 centimeter cell, what are you going to get if you measure that same solution in a 10 centimeter cell? So you remember that with Beer's Law that absorbance is directly proportional to path length. So if you're looking through 1 centimeter, if you look through 10 centimeters, what you'll get is a reading that's 10 times higher. And so that would be a reading of an absorbance reading of 7. Remember I kept talking about a linear range? Well, what I had one of the groups do in lab 2 last time is I said, why don't you add 70 mils of dye and see what happens? So they added, who was in that group? Okay, so you added 70 mils of dye, and here's the reading. It's an absorbance of 4.0. Here's the rest of that dilution series. Would you say that fits on the curve? No. So you're outside of the valid range. And you remember that we're dealing with log scales. So an absorbance of 2 means that 1% of the light is being transmitted. So an absorbance of 7 would be almost 0 light getting transmitted. And we get into a signal to noise problem with the detector. There's almost no light hitting the detector. So you want to make sure that whenever you use an instrument, you want to know what the valid range is, and sometimes just do a little experiment and see if you can get beyond the valid range, so then you know. And so this is a beautiful example of the nonlinearity. You violated the principles of Beer's law. So when I say that Beer's law, that you can use that absorbance to get a concentration with the following caveats, that it's in the linear range, that it's a non-scattering solution. And so this is a really great example, and I appreciate that group who did that little experiment. Just to beat it home, because we're going to be doing this today. So here's Beer's law. The lecture is on the class website. If it's the same chemical, so the molar absorptivity is constant. If the path length is constant, the absorbance is directly proportional to the concentration. And so that's what you're going to do in the lab today. You're going to hold the path length constant. It's going to be the same solution, and you'll be able to generate a standard curve so that you can translate absorbance into concentration. Remember, absorbance is unitless, and so you need a translating factor in order to go from a unitless number to a concentration with SI units. Okay, so that's what we'll be doing today. What I want to do is passing around the room are 6 trays with my salt collection. I love salt, and there's salt from Denmark, there's salt from Iceland, there's salt from Cyprus, which is the red, which has beautiful, beautiful crystalline structure. And when you go to the grocery store, and then there's a block of Himalayan sea salt, I don't know where the sea salt, that block of pink salt is, that's been mined, and yeah, you can pass it around. Don't, it came back to me, Max, maybe make sure I get it. It's pretty heavy. And so, you know, we take salt for granted. You know, salt is in our blood. Salt, the history of civilization, before people got efficient at concentrating salt, you couldn't carry out wars except locally. But once you could preserve food with salt, then the whole history of conquest began. And so it's sort of interesting if you look at conquest and commerce. There's a lot that's completely intermeshed with salt. There are 6 ions that make up, and this is trying to show graphically, here's our meter cubed, showing the proportion of salt ions that make up seawater. So for seawater that's 35% salt, it's dominated by sodium chloride, magnesium, calcium and sulfate, potassium, and I have the concentrations. I think it's a little bit easier here. And so notice these are all millimoles per kilogram, which you could call millimolar, but can you think of a reason that in the ocean you might want to report them as kilograms? Have you ever seen a styrofoam cup that's gone down on Alvin? Starts out like this, you go down 6,000 feet, and it comes back shrunk, and that's because of pressure in the deep ocean. So there's a potential ambiguity because a volume that's a liter at the surface can get compressed at depth. And so rather than reporting in volume and say, well, is it volume at depth or is it volume at the surface? If you make it independent of getting squished, then you don't have that ambiguity. And so we try to resolve ambiguity. And so what you'll see in the modern literature is moles and sometimes grams, but very often, you know, moles per kilogram. And a kilogram of seawater at the surface is just about a liter. Sodium chloride is the biggest one. This is probably some of you have read books by Mark Kurlansky. This is a really fun one on salt, and it goes into the history of salt. So here are these ions that are in the millimolar range. But there are also a lot of other ions that are in the micromolar to nanomolar range. These major ones are what we call conservative, and so that means that their relative proportion is constant with they relatively have a relative proportion as a function of salinity, whereas elements like nitrogen and phosphorus and silica and trace metals are lower concentrations, and they're called non-conservative because they get used by bugs. And by bugs, I mean phytoplankton, bacteria, and get transferred up the food web. Highest concentrations of nitrogen in the ocean are probably about 40 millimolar. Phosphate, probably about 3, and this is like the deep, deep sea. Silica really varies as a function of whether or not it's close to volcanoes or hydrothermal vents. This is used by diatoms. Nitrogen and phosphorus is used by all phytoplankton and is essential for life. And these are lower concentrations compared to these major ions. And so they're lower concentrations, and they sometimes can be used up by the living organisms. And they potentially can limit the biomass. So one of the things that we're going to do in the experiment next week is you're going to look at the growth rate of phytoplankton with different concentrations of phosphate. And you're going to explore whether or not different amounts of phosphate in different cultures change the ultimate biomass that you can get in a culture bottle. So these are limiting nutrients because they're at low concentrations and they can be depleted, and they're essential building blocks of life. Now, if we go back to total salinity, the salt that you're passing around, where does it come from? And I asked one class 5 years ago, I had a jar of salt from the grocery store. And I said, where does this come from? And she said, at the grocery store. And I go, yeah, that's where I got it. But where does it come from? And she said, they make it. And I said, oh, out of what? Well, out of sodium chloride. Well, where do they get it from? So here's where they get it from. So some of the salt comes from weathering of the continental crust. Now, as we start, there will be different periods in geological history and maybe in modern history, because weathering is weathered usually by water. And so in really wet periods, there's going to be more weathering of the continental crust. But this is one source of salt. The other one is hydrothermal vents. And this is particularly true for trace metals, that they're really an important source in the ocean for trace metals. And then what stays there is a function of the chemical equilibrium. Salts that are less soluble are going to precipitate out, and salts that are more soluble, like sodium chloride, are going to stay in solution. So like that picture right at the beginning of the lecture shows what's called evaporites. And so there's actually evaporation of salts, and you can get those accumulations, which then you can mine. So that salt on your table, most of this salt that's going around the room is actually from the modern ocean. That block of pink salt is from the ancient ocean. And sometimes they come from ancient lakes, and so they're in geological time, there's been evaporation. And my husband's uncle, he's Latvian, was sent to Siberia during World War II, right after World War II, to work in the salt mines. And he worked in the salt mines in Siberia. And that's what, growing up, you used to hear, well, if you're bad, you're going to get shipped off to work in the salt mines. That's because you worked in underground. And it wasn't particularly nice. Now today they do it with machinery. But the ancient ocean, you find these big deposits of salt, and they're mined. Up near Oswego, New York, I think that there's a lot of salt springs, and they used to make salt there. The modern ocean Typically, they get the salt by evaporation, and now it's very foo-foo that you have all these stores that will sell olive oil and they'll sell salts, and then they start adding stupid things like Merlot to salt. You've got some black salt from Hawaii that actually has lava flakes. So they're evaporated either by the sun or by fire. And there's actually a place on Mount Desert Island where the guy goes out into the middle of the Gulf of Maine and he brings back barrels of water. And then he's got these little greenhouses and food-grade plastic, and he pours all the seawater on there and evaporates it, and you can get Gulf of Maine salt. So if you're looking for a present for your parents, if you're not from Maine and you want to say, hey, this is, and you can pay $5 for this little jar that says Gulf of Maine salt. If there's a lot of fuel, this is effective. If there's a lot of sun, this is effective. In Iceland, they only make salt during the summertime, obviously, because that's the land of the midnight sun. If you pull a vacuum on it, you can actually get a really fast precipitation schedule. What the Russians do, because there's not a lot of sun and there's not a lot of fuel up in the tundra, is they freeze it. And so when you freeze seawater, it extrudes a brine, and so they concentrate that brine, and then they heat it up. And remember, we can go to the grocery store. In 1,000 years ago, salt was life, worth your weight in salt. It was expensive and it was necessary for life, and that's how you preserve food if you wanted to make it through the winter. So here, if you want to go to a place like Dubai, where all of their fresh water comes from desalinization, the way you get a liter of water is you get a liter of brine. And so then what do you do with the brine? Well, usually you pump it back in. You're causing stratification. So think about it as marine scientists. You may want to go to some exotic country and, give them some tips in terms of, okay, if you're pumping all this brine back into the ocean, you now have a super stratified benthic layer. What's that going to do in terms of the food web? What's that going to do with the, organisms that need to go down to the benthos? So it's a really interesting question. If you remember some of those, let me just show you this. So here's one type of salt pond. There's a beautiful picture from France that shows flamingos walking through it. And then there's a picture right next to it that shows a very highly aseptic environment. Well, I don't know. When you buy your naturally evaporated sea salt, think about the beautiful flamingos going through it, because as it gets briny, brine shrimp will grow there. So here's evaporation. Here's an example of doing things by fire. And then there's the highly industrialized. So it's pink because you still get algae growing in it, and Denaliella changes its pigments, more carotenoids when it gets more salty, so you get some of these pink colors. But what Cargill does is they do a lot of vacuum evaporation, and different salts have a different precipitation schedule. So like if you're driving around in Maine, calcium chloride is what they put on the roads, and so they get calcium chloride out as part of this whole precipitation schedule. And so what you buy in the grocery store, Morton's salt, is different than the salt that you get from the ocean, because if it has any value, they have taken it out. They add iodine back in, but they've taken out anything that has any kind of value. And I think it's bromine that it doesn't precipitate, and it has a horrible, horrible smell. And there was a graduate student back in the 1700s who discovered it, and he named it, and I can't remember what he named it. It was something stinky, but his advisor didn't like the fact that the graduate student discovered it, and so he took credit by changing the name. But it was very bitter in terms of its taste. So different salts, obviously have different tastes, and salt is it's a big business. Here's some kind of cool links. I think all of them still are enabled. I forgot to check this year. But anyway, you might want to just check out if you get intrigued by salt. And I forgot to put the best slide up there. In Poland, is anybody Polish? Okay, did you ever hear of a salt mine in Poland where they actually, did you go there?
Yeah.
How do you pronounce it? It begins with a W.
Oh God, I don't remember how you pronounce
Yeah.
it, but they had salt mines deep in a cave, and you walk through it, and they have sculptures made out of salt.
They have a cathedral with
Yeah.
chandeliers made out of
You
salt.
can't take any pictures, and like you just walk around. You can even lick the walls if you wanted.
Wow.
Because
Wow.
that's gross because you don't know who licked it.
But they used to bring horses down there, like the draft horses, and the draft horse would go down and never come up, because they worked down in the dark for 25 years. But I really want to see this cathedral in Poland. I don't think it's open in the wintertime, but it's completely made of salt. And so that, I think, yeah, just Google Poland salt mine cathedral, and you'll get some fantastic pictures. So salinity, let me just talk a little bit about salinity. So salinity is the mass of dissolved salts in seawater. It determines the density, the freezing point. You know that lakes get, as they get fresh water, as it gets colder, they get denser until it gets to 4 degrees C, and then it gets lighter. Well, not so with seawater. As seawater gets colder, it gets denser. And it just keeps on getting denser. That's why the ocean doesn't freeze for the most part. So salinity affects freezing point, and the TS characteristics, which in Dr. Thomas's class next year you'll be really exploring a lot, are used to designate different water masses. So they're like fingerprints of different water masses. So salinity is the mass of dissolved salt in a kilogram of seawater. If you're a history buff, this is a really fun website, and it goes back to Socrates and Aristotle in terms of salinity. And, again, you open a textbook, and it talks about salinity. Well, it's really hard to measure it directly. So I would think if I want to measure the concentrations of salts, if any of you have taken analytical chemistry, you reduce it, you evaporate. Well, if you've ever tried to evaporate salt, it's really kind of hygroscopic, and it's sticky, and it's really hard to get rid of the water. But if you dry it, you volatilize some of the compounds. So you either have water in it, or you get rid of some of the compounds by heating it. To get rid of the water, you get rid of other things too. So what they did up until the 60s is they titrated the chlorinity, that's the chloride ion, because remember, sodium chloride dominates salt in the ocean, with silver nitrate, and they precipitated silver chloride and calculated salinity, and this is based on the chemist who developed this in the 1860s. So it was based on a precipitate of silver chloride. That's a little bit time consuming, and if you want to do a continuous profile of salinity, forget it. You're going to take many, many students and chain them to a desk for many years and have them making all these measurements. It's not going to work. So salinity, but in the last 50 years, they measure it as conductivity relative to standard seawater, and that used to be Copenhagen water that they collected right out of Copenhagen. And now there's an international group that will sell you standard seawater for $200 a vial. And now it is referenced the conductivity relative to sodium chloride, 36 grams per kilogram. And it's a whole lot easier to measure out sodium chloride. You measure that, and then you can use that as your standard. Now, what are the units? Remember, this is mass per kilogram? Well, it used to be parts per thousand. You ever see parts per thousand for salinity? And then somebody brilliant got to the idea, well, if this is mass per mass, it cancels. So if you have mass per kilogram, well, kilogram is mass, so that cancels, so it's unitless. So we talk about a salinity of 30. Well, first they called it practical salinity units, and then they said, okay, because it cancels, there's no units. So my salinity is 30. And everybody hated it. So now people have again changed the units, and it's milligrams per kilogram. even though they cancel, they retain them because you know exactly what you're talking about. So if you want to dazzle Dr. Thomas next year, you know, salinity has now gone back to being milligrams per kilogram. And here's the citation. And it just shows that this whole idea of units and improving measurement isn't static. Did you know that you can measure salinity from space? You do it in these far X bands, and the US, NASA had a satellite called Aquarius that died last year, but it operated for about 3 years. So if you look up NASA Aquarius salinity, you can see salinity on a monthly basis for about 2 years over just about the entire ocean, which is really pretty exciting if you're talking about changing hydrologic cycles and how some places in the ocean might get saltier. But anyway, you should know how salinity is measured, and it's now back to milligrams per kilogram. Damariscotta River depends on freshwater flow, is any place between about 20 and 30. You go into the Gulf of Maine, salinity is between about 30 and 32 milligrams per kilogram. So phytoplankton nutrients, we have, back about 4 slides ago, talked about 2 potentially limiting nutrients in the ocean. That's nitrate and phosphate. And both are fundamental to life. And in the lab, we're going to measure phosphate concentration. And the question for you is, I was going to bring in a jar of water, but I think this will do. They're colorless. So how do we measure them with a spectrophotometer? That's the question. But first, you walk downstairs on the 3rd floor, right across from the heads, you'll see the periodic table. Here's nitrogen, an atomic number of 7, mass of 14, although there are some isotopes that are N15 and N13. Primarily in the ocean, you find nitrogen as nitrate and as ammonia. Ammonia is a regeneration product from zooplankton excretion after they metabolize, fish excretion, etc. And it's highly reduced, so it is preferentially taken up by phytoplankton and bacteria. Nitrogen is the backbone of proteins, which are the enzymes, and it's also the backbone of nucleic acids. So it's essential for life. And one of the things is it's transparent, invisible wavelengths, but let me show you the absorption spectra. It does absorb at in the deep UV about 220, and in the last lab, these are some instruments that people use on moorings and on profiling floats, and Dr. Townsend has been doing a lot of work with these detectors that you use the UV absorption of nitrate to put on moorings. And if you run into him in the hall, ask him how his ISIS and SUNAs are doing. I think they're mostly SUNAs now, and I can't remember what SUNA stands for. But so what's the source of nitrogen? Once again, we are changing the balance of nutrients in the world because the 2 natural, non-human ways of getting nitrogen. So 80% of the air is diatomic diazonitrogen, which is a really, really stable bond. But lightning can break that bond, high energy lightning, and cyanobacteria are capable of converting nitrogen. They can break this bond. It takes a lot of energy to make ammonium. So historically, the 2 ways that nitrogen has become biologically available is through nitrogen fixation, which is biological, and lightning. But since the 30s, man has been making nitrogen for fertilizer and for bombs. And the industrial component is now equal to the biological and the atmospheric component in terms of the generation. So we have doubled the input of nitrogen into the ecosystem through this industrial process called the Haber process, which also takes a lot of energy. In the ocean, you sometimes see zero, particularly after the spring bloom. If we go down to the bottom of the Marianas Trench, it's about 40 micromolar. If you go to Chesapeake Bay, it might be like 100 micromolar. Dr. Wells went to a river in China, and his colleague was measuring. There's also another form that is an excretion product. Let me see if I can get the chemical. Oh, geez. There's two ammonias. Let's see. I think this is urea. That's one of our excretion products. And usually in the ocean, it's like less than 1 micromolar, maybe even 0.1 micromolar. Well, in this particular river, it was 600. And the person who went sampling it just about died because it was overwhelmingly, horribly smelly, and it also volatilizes. So it is possible where there's pollution from sewage and other applications that, like pig farms, North Carolina pig farms. You get these holding ponds, and then when there's a hurricane, the holding pond gets breached, and then you get all of this nitrogen that goes into the estuaries. So this is sort of the typical range, 40 micromolar in the deep ocean, but you can get much, much higher. And when that happens, things get out of whack. And we'll talk about some of the implications of that. Okay, phosphorus, atomic number is 15, the weight is 31. These are radioactive isotopes, P32 and P33. Very low concentrations in seawater, usually less than 3 micromolar. So when you measure the water in 2 weeks, you can tell us what the winter surface phytoplankton, surface phosphate is right off the mouth of the Damariscotta River. So you'll be measuring that for year 0. Critical for nucleic acids and for membranes. And the energy source in the cell is adenosine triphosphate. And so phosphate is an absolute essential element for anything that's alive. And where does it come from? Again, weathering of rock. And over geological time, as I said, more wet times, you get more weathering. So more phosphate goes into the ocean. So we may be entering a period where there'll be more phosphate going into the ocean. 0 to 3 micromolar, and again, due to pollution. And what happens when there's phosphate limitation is you sometimes get the phytoplankton form these different kind of organic compounds and excrete them. So in the Adriatic, it's very phosphate limited. There's a lot of calcium. And you see the scale of this is a diver. They have these aggregates that form as a function of phosphate limitation. And they can be the size of a VW bus. And the first earliest report was in 1793 that these washed up on the shores of Trieste, Italy. And they get them as a function of phosphate limitation. So when phosphate is limiting, the phytoplankton tend to make some very funny and very, very sticky organic compounds. I don't know if you've heard, water is the new oil in terms of fighting over. Mark Twain used to say, whiskey's for drinking, water's for fighting over. well, I think we're going to start running out of phosphate, and that is the looming prospect. The way that they get phosphate, so for making fertilizer, is they actually mine it from these ancient deposits. And if you look at the different sources of phosphate, green is manure. You can barely see this little orange line of human excretion. The red line, which you can kind of see, is guano from birds. This is mined phosphate. And so people are talking about, you know, we dump things into the ocean rather than recycling it. And there have been estimates of running out of phosphorus in the year 2050. So anyway, again, you know, these are things that you need a smart person to address in terms of how do you do a better job of recycling. So back to the question. If phosphate is as colorless as your water, let's forget the fact that you have it in an orange bottle. If somebody has a clear bottle, you could look at it and say, you know, this is what seawater looks like. It's clear. So nitrate is a special case because you can measure it in the UV, but phosphate is clear in the UV, in the visible, and in the IR. So how do you measure it? Two things that you have to keep in mind. One of them is Beer's law, and the other one is stoichiometry. So Jeremiah Richter came up with the term stoichiometry when he defined what he called the law of definite proportions. And so that says what's on this side of the equation balances what's on this side of the equation. So carbon on this side, and this is photosynthesis, is in stoichiometric proportions on both sides of the equation. The same thing with the oxygens. So that in marine sciences, we can use, if you have a chemical reaction, both sides of the equation are going to be in balance. It's this stoichiometry, quantitative proportions, or the mass ratios involved in a reaction. We can use that to measure the concentration of phosphate by complexing phosphate with something that's going to turn it into an absorbing material. And it's done in a stoichiometric way. So the amount of a complex is going to be, the amount of a complex that you're going to produce in the lab today is proportional to the amount of phosphate that you had in your test tube. So we're going to use it to measure nutrients, and then next week we'll talk more about how we can use it to predict phytoplankton. And we'll go back to Alfred Redfield, who was at Woods Hole Oceanographic in the 30s, where he said that in the ocean, the ratio of nitrogen to phosphorus was about 16:1. Carbon to nitrogen to phosphorus was about 106 to 16:1 on a mole to mole to mole basis. And next week we'll explore how we can use measurements of phosphate to predict how much phytoplankton carbon we're going to get. So we'll do that next week. But this week, what we're going to do is form a chemical complex that has a stoichiometric relationship with the nutrients. So we're going to form a complex, and the concentration of the complex is directly proportional to the concentration of phosphate. This complex absorbs light, and so we can measure it. We're going to hold the path length and the molar absorptivity constant so that the absorption of the complex is proportional to the concentration of phosphate. So that's how you measure a colorless solution. Here's the absorption spectra, 500 to 1,000. So it does absorb a little bit in the green, but the maximum absorption wavelength is 885. And these are just different concentrations of that complex. And so it's going to turn blue because blue light is not absorbed, but you want to make sure that you measure the absorption at the maximum wavelength, which is 885. And some of this stuff, antimony, molybdenum, there's sulfuric acid in there. It's a little nasty. That's why I want goggles, because if you get a drop of that in your eye, it's not a really good thing. If you get a little bit on your clothes, you could burn a hole in your clothes. So if you have a favorite shirt, yeah, you might want to think about changing it. So I'm going to ask you to wear, when you're touching this stuff, to wear gloves and goggles. I tend to be a little paranoid, but paranoia is not necessarily a bad thing. Okay, so here's just, putting it all together. Why do we use standards? So I said the absorption is related to the concentration of the complex. We use standards because absorbance is a unitless number. So we use standards so that we can convert absorbance to SI units of concentration. We have a second type of blank, and this is where people very often get confused. Distilled water, milky water, is the instrument blank. You're also going to do a reagent blank. And that reagent blank is pure water, milky water, plus this reagent of antimony, molybdenum, etc. You add the reagent to everything, including the blank, because there's some absorbance associated with the reagent that's not associated with phosphate. So people will, and I guarantee you, somebody will forget, you add the reagent to everything, including to water, and then you're going to subtract it from everything. And that includes your samples. You're going to subtract this from your sample absorbance and from your standard absorbance. So we have two types of blanks, and they serve two different purposes. And here again, if you forget, it's in the lecture on the website. If you're asked a question on your homework, this is where you would go to find out. I'll ask you time and time again. Here's absorbance versus concentration. This is your standard curve. You have to measure a standard curve every time because the efficiency of your reagents will change. And so when do you do a blank? Every time. When do you measure standards? Every time. You're going to generate something like that. And I'll see you in the lab. And if people who have salt at their table, if you would be so kind as to bring it up here, I'd appreciate that.